Okay, everyone, we are going to get started, and we're definitely dwindling in numbers yet again. And I did warn people that this was not a lecture to miss, because we're going to cover a couple of things that are slightly tricky. So you guys are in the right place right now. Okay, so we're going to talk today about ocean circulation. And my favorite image to do with this is our little rubber ducks. About, when was it? It was in 1992, a big container ship left China, and one of the containers happened to be full of little rubber ducks and little crocodiles and other things like that. And unfortunately, one of the containers containing these got swept overboard and released fleets of rubber ducks into the North Pacific. And ever since then, we've been finding them along coasts. They're just sort of sailing along. And since then, we found them in Australia and South America. They've actually made their way through the Arctic Ocean, locked in sea ice, and have popped out the other side. And so we can tell, we know sort of that the ocean is moving, and we're going to look at how it moves. And in particular, we're going to look at the surface movement and then the deep movement, because they actually function very, very differently from each other. So I have a lot of announcements to start with. So quiz 6 is going to be available from 2 p.m. today until 1 p.m. on Tuesday, because Monday is a holiday. And I know that people have plans, so you have another day to complete the quiz this week. So do have it done by 1 p.m. Tuesday, and I'll release the results immediately so that you can sort of study from that. And the reading is up there too. Midterm 2. So I made a mistake in the note from Wednesday. I said it was an HIB 100. It's not. It's in this room as normal. Okay, so it's in this room on Wednesday from 1 to 1:50. Please be on time. And it's just like last time, half multiple choice, half short answer. You're more familiar with the sort of things I like asking now. It covers the atmosphere and hydrosphere lectures, which are 10 to 18. And there's a few small concepts I'd like you to be familiar with from the first part of the quarter, and they're listed on the study guide. Assigned seating, that's pretty self-explanatory. You are allowed to bring one double-sided 3x5 note card again, if that would be helpful for you. I have updated the study guide. So on the class website now, the study guide has a few things crossed out. So we didn't really talk about lakes, so I've crossed out lakes. And there's a couple of other things that we didn't talk about. So if you go back and have a look now, you'll see a few things crossed out that you don't need to be aware of. I've also uploaded a whole bunch of practice questions. And there are 2 documents. There is one which has just the questions for you to work through, and then another document with the answers to those questions. And I really would encourage you to challenge yourself to work through those questions before cheating and looking at the answers. Okay, you learn much more that way. You can get a sense of what you understand. It loses some of its value if you just look at the answers. Okay. I've also reopened all of the previous quizzes, so you can use those to practice. You can fill them in as many times as you like now, quizzes 1 to 5, but not quiz 6. Quiz 6 still needs to be 3 times only. Okay. And I'll be in my office from 9:30 to 11:30 on Wednesday if you have any last-minute questions. The TAs are also holding a review session in HIB 100 from 7 till 8 p.m. on Tuesday, which I know is late, but that was the earliest we could get a room this big. Okay. Does anyone have questions about the midterm for me? No? Okay. One last thing then. Discussion activity for week 7. So half of our discussion groups actually meet on Monday, which is no good next week because Monday is a holiday. But we've been learning about the ocean and water, and I wanted to encourage you to actually go to the beach. So you can earn credit next week by going to the beach and filling out some of the worksheet that I've put on the class website there. So you can download it. It's sort of, yeah. So the things that I want you to do is things like look at the cliffs and look for life. And if you just go to Newport Beach, you can't really find life other than people, really. So it tends to be much better if you can go to Corona del Mar, which is just around the corner from Newport Beach. So you can usually park up there or cycle around. Crystal Cove, if you haven't been to Crystal Cove, it's a really beautiful state park, but they do charge you quite a bit for parking. So if you have a group of 5 people, then I think parking is $15. You can get so $3 each, but otherwise it is a bit pricey, I'm afraid. But they are beautiful places to go, and it's a nice time of year to go as well. Okay? So if you can find a beach with cliffs, you could go there instead. Okay? Any questions about that? Okay. So let's look at the ocean, and the ocean moves, and it's really very important that the ocean does that because it transports heat around the Earth, and it helps even out these differences in heating that we get due to the curvature of the Earth and the atmosphere. And atmospheric circulation drives surface ocean circulation. Not deep ocean circulation, but at least the surface ocean circulation, but not in a simple way. Okay? If you blow across a sort of saucer of water, if you blow across a puddle, water will move with that sort of air sort of forcing across the top. But on very, very large scales, we need to start taking into account the Coriolis force again. So just like we use the Coriolis force in the atmosphere, we also need to consider the Coriolis force for water, because the water isn't attached physically to the Earth, it's sat on top, and so as it moves relative to the Earth's surface, it gets deflected. Which way in the northern hemisphere? To the right, and then the left in the southern hemisphere. So you can see that I've drawn the winds, or I haven't, but the winds are drawn on there in green, and you can see that the surface currents marked in red for warm surface currents and blue for cold surface currents. You can see that they don't necessarily go absolutely along with the wind. The exception is at the equator. At the equator, remember, we don't have Coriolis force. It's maximum at the pole and minimum at the equator. And so water just goes with the wind at the equator. But elsewhere, we have to start taking the Coriolis force into account. So we're going to talk about 2 things. And if you can get these today, then that would be very good. So wind moving across the surface of the water causes that water to move. So there's drag, there's friction. That movement of wind across the water causes the water to move. Okay? But if we are to look down and sort of look at the directions that the water is going in, at different depths, actually the water is moving in a different direction from the wind, and it actually spirals as we go down. We call this an Ekman spiral. And because it's too complicated to try and think of all our ocean currents spiraling, what we do is we add up all of those different directions and the different amount of movement in each of those directions. And if we add it all up, it's more or less 90 degrees to the left of the wind in the southern hemisphere and 90 degrees to the north of the wind, 90 degrees to the right of the wind in the northern hemisphere. And I want to draw this out for you because I think it's much more helpful if we draw this. So, pens and paper out. So I'm going to look at the top 10 meters of my ocean to begin with. So I'm just going to take my top layer, okay, and I'm going to have my wind direction moving this way. Okay? So if there was no Coriolis force, which way would my water move? Yeah, with the arrow. It would just go in the same direction as the arrow. So that's my wind, okay? And that's in the top sort of 0 to 10 meters or so of my surface ocean, and this is our wind. In reality, we have to take the Coriolis force into account. And let's say that we're in the northern hemisphere. What direction is the Coriolis force going to act in? Yeah, 90 degrees to the right. Okay, so 90 degrees to the right of that. So here's our Coriolis force. And so our water will actually end up traveling in between those two. Okay, so that's our water. So that's our top 10 meters or so. So let's think about what happens in the layer immediately underneath. So here's now 10 meters to 20 meters. Is that water feeling the wind? No, because it's actually much further down. It's not in contact with the wind at all. What is it in contact with, though, that is moving? The water above. So now, the direction that the water above is going in is this direction. Okay? So our force trying to get this water to move is now wanting it to go in this direction. But we have our Coriolis force. What direction does our Coriolis force act? 90 degrees to the right. So if we go at 90 degrees to the right of this arrow, okay, here's our Coriolis force. And so our water is going to end up between those again. So it's going to end up going more in this direction. Okay? And then one more layer just to drive this home. So in 20 to 30 meters, what's driving the movement here? The overlying water, which is going in what direction now? Off to the side. So this is the direction of that overlying water. So now the force trying to get this layer of water to move is in this direction. The Coriolis force acts at 90 degrees to the right of that. Okay? And so our water will end up moving in this direction. Oops. And what you'll see is that it's not sort of perfectly, that force of the wind isn't perfectly translated down each time. We lose a bit of movement as we go deeper and deeper. Yes?
Does the water below affect the water above it?
Not in our example. And so what happens is that we get the most movement at the surface, and then we get a little bit less in the next layer down, a little bit less movement in the next layer down, a little bit less. So by the time we're sort of 100 or 150 meters down, the water's hardly moving at all. But what's happening is if we look down from above, we'd see that the wind is going off in this direction. Our surface water is going in this direction. The layer underneath is going in this direction, but slightly less. And the underneath is going in this direction. So it ends up spiraling round. That's our Ekman spiral. Okay? But if we add up all of these little arrows going in different directions, then we can make life a lot easier for ourselves. And what we can say in the northern hemisphere is that if this is our wind, our water is going to go at 90 degrees to the right. If we add up all of that spiral and average it out, our water goes at 90 degrees to the right in the northern hemisphere. And if we had the same wind in the southern hemisphere, the water would go at 90 degrees to the left. Is everyone with me so far? Yeah? Hopefully? Okay. So, if we go back, what I've done is I've written a little explanation for you. So hopefully that will make sense. It's an important sequence of information. And my question for you is this diagram showing what would happen in the northern hemisphere or in the southern hemisphere? Okay, a few more seconds. Right. Good work, guys. Yes, absolutely. So we're going to the left. So our wind is in this direction, and our net water movement is being deflected at 90 degrees to the right. So we're in the northern hemisphere. If we're in the southern hemisphere, the water would be spiraling in the other direction. Okay? So that's the first really tricky thing to get, I think, and I think you guys have got it. So the movement of the surface ocean and the deep ocean as well on Earth is complicated by the fact that we have big blocks of land in the way. We have our continents, and they interrupt the movement of the surface ocean. And what happens is we get two things that result from this. So first of all, we get vertical motion of water. So we have upwelling and downwelling, and we'll talk in more detail about this in a second. And we also get what we call gyres, and we're going to come on to that in a second as well. So both of these are vertical movement of water, so upwelling and downwelling, and our gyres are a result of continents that get in the way of this movement of water. So first of all, you can see that on my diagram here, I have my wind going along the side of my continent. Which way is the water going according to Ekman transport? 90 degrees to the right, okay? And so because of that wind, the surface water is moving away from land. So if all my surface water, if the top sort of 100 meters or so of my surface water is moving off land, or sort of offshore, am I going to end up with a giant hole in the ocean next to my continent? No, okay? What happens is that we have to replace that water. And we can't replace it from the side because all the way along that continent, our surface water is moving away. We can't replace it from above because it's the atmosphere, there's no water up there. We can't replace it from behind because the continent's in the way. The only place we can replace that surface water from is underneath. So because we have this surface water moving away from land, we would leave a hole behind, and we can't do that, so water is pulled up from underneath to replace that, and we call that upwelling. In our second diagram, if according to our wind, which is now going in the other direction, which way is the water moving? It's moving at 90 degrees to the 90 degrees to the right still. Remember, you have to look along the direction of the arrow, and it's still moving at 90 degrees to the right. So it's now actually moving onshore. So we have our top 100 meters or so of water being forced by this Ekman transport at 90 degrees to the right of the wind onshore. Is that 100 meters of water going to hit land and keep going over the continents to the other side? No. So it has to go somewhere. It can't go up. The only place it can really go is down. So where we have water moving offshore, we have upwelling. Where we have water moving towards land, we have downwelling. And there seems to be some silence here. So let's see if you guys can get this. So what would be happening along California? So there's my wind direction. We are in the northern hemisphere. So think about what direction water would be going in. And then think about whether you'd get downwelling or upwelling as a result of that. So don't just sort of click wildly. I'm going to give you a minute to think about it, talk to your neighbors, think about directions, and then I'll ask the question. Okay, so hopefully now you have an idea. So answer my question and we'll see how we're doing with this. So just a few more seconds. Okay? Not good enough. 60-40. Okay, so let's see if we can get our ratio a little bit better than that. So here's one I just drew, which is not terribly pretty, but here is the USA. Here is our wind direction. We are in the northern hemisphere, so which way is water going to move? Is it going to move away from land or is it going to move towards land? Remember, when we're talking about the Coriolis force, we have to look along the arrow. So if I look along the arrow, do you want to change your minds? So which way is water going to be moving? It's going to be moving away from land. Okay, so because of the wind that comes down the coast, we get our water moving offshore. Okay? So now, let's go back. And I'm going to ask you the question again. Should be nice and quick this time. So, is upwelling or downwelling happening off California? So we'll double check where people are getting lost. Okay, a couple more seconds. I think we've got most people. Right. Oh, much better. Great. Okay. So yes, we have upwelling happening along California. So given that that was a bit of a challenge, let's do something a little bit spontaneous. So how about, now I have land, okay, this is my land, and we're going to have wind going in this direction. Okay, so this is our wind, and now we're going to be in the southern hemisphere. Is upwelling or downwelling going to happen here? So A for upwelling, B for downwelling. Okay, so let me, oh, I can't ask the question, unfortunately. So think for yourself and come up with your answer, and then I'll come back and answer the question in a second. Okay, so feel free to vote, even if it doesn't appear at the top. Do vote, because I can see the results at the front here. So a few more seconds. A few more seconds to vote. Okay, so let's take a look at our results. So 77% of people said upwelling. Oh, sorry, downwelling, thank you. Sorry. And 23% of people said upwelling. Okay, so let's see if we go back, who was right? So we're in the southern hemisphere. Which way is water going to move due to our wind? To the left. So our water is going to be moving in this direction. Okay? And so you're right that we're not going to have water moving on shore and over the mountains to the other side. It has to go somewhere, and it's going to sink back down. Okay? So it's moving towards the land, it's going to sink back down. Great, I'm really impressed with you guys. This is good. Okay. So, of California, we said that we had upwelling. And I wanted to remind you that, remember, the limiting factor for life in the surface ocean isn't light, it isn't CO2, it isn't water. The limiting factor is usually nutrients. So things like phosphorus or nitrogen. That's usually what limits the amount of life we see. And so we don't have many nutrients in the surface ocean often, but when all that organic matter sinks and decays away in the deeper ocean through time, we build up nutrients in the deep ocean. And so where we get upwelling, where we get movement of this deep, old water up to the surface, we bring nutrients back up. And so we get amazing amounts of life. And certainly that's what we see in California, is we see that this southerly wind coming down the edge of our continent drives water offshore, and so we get lots of upwelling. And not only does that upwelling water bring up lots of nutrients, but it's also really cold. It's one of the reasons why California has really cold oceans compared to perhaps on the East Coast. Okay? It also does things like make fog more likely, the fact that we have this sort of colder water around. Okay. So now I wanted to talk about gyres. So that was talking about vertical movement, so upwelling and downwelling. Now I just want to talk about what's happening in the surface. So these are really basically the same concepts that we were talking about with high pressure systems and geostrophic winds. So to start off with, I have, so my little schematic at the side here is basically representing the North Atlantic. So I have land on one side, which is sort of the US and Canada. I have land on the other side, which is Europe and Africa. And because of our three-cell conceptual model, do you remember we had more or less easterly winds going along near the equator? So down here we have our easterlies to the south near the equator, so winds moving in this direction. And then because of our Ferrel cell, and we had winds moving in the other direction, we have westerlies to the north. Okay? And so what happens, so what hemisphere are we in? We're in the northern hemisphere. So what direction will water move in due to the westerlies? Are they going to move up the page or down the page? Down the page, yes? So our wind is going in this direction. We're going to act at 90 degrees to the right Ekman transport is going to move that water down towards the middle of my page here, in the middle of the Atlantic. Well, what about my easterlies to the south? Which way is Ekman transport in the northern hemisphere going to drive water due to those easterlies? Up. Okay, so 90 degrees to the right of that arrow, which is up again. So what happens is that those different wind patterns both act to push water towards the middle of the North Atlantic. Okay, so water piles up in the middle of our North Atlantic. And water doesn't like being a pile. Yes?
Why does the southern hemisphere go to the right?
So we're not in the southern hemisphere yet. We're still north of the equator. The equator sort of runs along the bottom of the screen here. So good question. We're still in the northern hemisphere completely. This is just the North Atlantic Ocean. So we have our pile of water in the middle of the North Atlantic, and water doesn't like being a pile. We don't pile up water terribly easily. So what happens is that sort of high of water tries to move out. It tries to go from high to low. It tries to flow outwards to counteract this forcing of the wind. But as it flows outwards, which way is it deflected in the northern hemisphere? To the right. So you can see that as we get water moving out of that little high area of ocean, it gets deflected to the right. And what we end up having is water moving around that area of high pressure, just like we would around an area of high pressure in the atmosphere, so that we've talked about last week. Okay? So we end up with our pressure gradient in water this time rather than air, and we still get deflection to the right in the northern hemisphere. Which way would the water be circling around if we were in the southern hemisphere right now? Yeah, to the left. So we'd be going out and to the left. So we'd spiral in the other direction. So we go nice and clockwise in the northern hemisphere, but counterclockwise in the southern hemisphere. And that's what we see. We have 5 big gyres, 4 definite gyres, and 1 perhaps questionable one in the Indian Ocean. So we have North Pacific, South Pacific, North Atlantic, South Atlantic. And you can see that they do flow differently. They go clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And this has quite an important impact on the temperature of the water, because you can see that where we have water flowing from nearer the pole back towards the equator, those surface currents are really cold. If you look up near California, we have nice cold water being brought down along our coast from higher up towards the pole. And that's another reason why our water off California is so horribly cold, and it gets colder as you go north as well. If you ever try and go swimming off San Francisco, it's extremely cold. So we have both upwelling, which lowers our temperature, but also we have this cold current as part of this clockwise circulating North Pacific gyre, which is bringing cold water down. And conversely, if we look at the east coast of the US, so in the Atlantic, we can see that actually there we have warm water being brought up from near the equator past that coast. And so that's why we get lovely warm water off Florida around there. Okay? And we don't have a gyre in the Southern Ocean because we don't have land to get in the way. So here's a little map of sea surface temperatures, which I showed you on Wednesday. And you can really see the impact that these gyres have. So you can see how the temperatures, especially here off the tip of South Africa, those temperatures really follow the surface circulation. So where we're bringing cold water from the pole back towards the equator, we see that pattern in the surface temperature maps. Okay? So definitely our overall pattern was it's warmer at the equator and colder at the poles. But these surface gyres have quite a strong influence. And especially along the east coast here, we have nice sort of dry summers and cold water, whereas in Florida they have really warm water and it's really humid and hot, and it creates a huge difference in the climate on either side of the US. Okay? And we actually have names for these currents. So the one that runs past us is nice and easier to remember. It's called the California current. It's the cold current that comes down our coast. And if you go over to the east coast, then what you have instead running along the surface there is the Gulf Stream. If you've heard of the Gulf Stream, that's the current that runs along there. Okay? So we have these two different things, and I want you to remember the Gulf Stream because it's going to come back in a second. So we can actually study the surface height of the ocean using satellites now, and we can see those patterns. We can see that the red colors here represent maybe the very red, most red colors perhaps represent 1 meter higher sea level than average, and those sort of blues and purples represent maybe 1 meter below the average. Okay? So we can see these changes in the height of the sea surface, and you can see that where we do get our highs tends to be in the North Pacific, the South Pacific, the North Atlantic, the South Atlantic, where we have our gyres, where we have those winds pushing air towards the middle and building a little local high. But you can also see that in both these maps from different times, we have areas of low. Where is our areas of lows? Where are our blues and purples? The Southern Ocean, absolutely. And also there's a little pocket up near Greenland. And here we've got much lower sea surface temperatures. And this is where our deep water forms. This is where we have surface water that becomes really cold and salty and dense, and it sinks. And it sinks right down to the bottom of the oceans. Okay? So those areas where we have lows are where we have deep ocean formation. Yes?
What do we have going on in the Mediterranean there?
In the Mediterranean, we have lots of evaporation going on.
Like
it's most likely.
In that pink spot?
Yeah, so we have lots of evaporation, and that evaporation makes it so salty that we actually also have deep water formation in the east part of the Mediterranean. So we have surface water coming in through that Gibraltar Strait between Spain and Africa, and then it comes along and is evaporating the whole time, and it gets really warm, and actually gets so salty that it will sink, and then it will flow back out through the Gibraltar Straits, and it forms its own little water mass when it goes back into the North Atlantic. It's a really interesting one to study. Okay, but unfortunately for our purposes, we're just going to look at the northern area, the North Atlantic, where we have that sort of purple area, but also the Southern Ocean. Okay, so remember I said the Gulf Stream was going to come back. So our Gulf Stream is that nice warm current that flows along the east coast of the US. And it's nice and warm because it's coming from the region nearer the equator. And as it sits there and as it travels north, we have evaporation happening the whole time. And so it's actually a really salty current as well. And as that nice warm salty current heads north, it hits sort of Europe, so it releases some of its heat and it keeps Europe nice and warm. It also provides a lot of our precipitation. And so by the time we get up to maybe Iceland and around Greenland, it's still really, really, really salty, but now it's got a lot colder as well. And you know that the most dense water is salty and cold. Okay, so it's going to sink. And so our coldest and saltiest water is going to sink. And it starts to form this sort of conveyor belt. So you can imagine basically all of the world's oceans as one sort of big loop of rope. And as you sort of pull down water as it sinks in the northern hemisphere, it basically pulls along all the rest of this water. Okay? And this is our enormous deep circulation. So we call this the thermohaline circulation. And it's not driven by winds anymore. It's instead driven by density. It's driven by changes in salinity and changes in temperature. It's nothing to do with the winds. Okay? And it's difficult, I think, to imagine it in 2D, but those yellow colors there represent surface currents, and those blue colors represent deep currents. And this is sort of more of a 3D view, and it shows how we have this really deep ocean water that's being formed in the North Atlantic, and then it flows all the way down the North Atlantic, around the Southern Ocean. Some of it comes back up to the surface in the Indian Ocean. Some of it makes it all the way around past Australia, up through the deep Pacific, and then it finally comes back up to the surface around the Northern Pacific, and then it makes its way back, warming up all the time around the surface and back up into the North Atlantic. So it's one big long conveyor belt. Okay? So that's our that's our thermohaline circulation. So thermo for temperature, haline for salty. So our thermohaline circulation. And what we're interested in studying is that this is the movement of the entire world's oceans. It probably takes 1,500 years for that water to sink in the North Atlantic, make it all the way around to the Pacific and back around the surface again. So it's really, really sort of large, long-scale processes. And what we want to know is what we're doing to climate now going to potentially change how much heat is transferred by this enormous sort of whole ocean scale circulation? Has it changed in the past? Can we find evidence for that? Okay? And what could cause the thermohaline circulation to slow down or stop? And so which of these things that is happening today do you think might cause that thermohaline circulation to slow down or stop? So remember, it's density driven. We want nice dense water to sink in the North Atlantic. So what could make seawater less dense and so prevent this sinking? Okay, a few last seconds. Okay, so let's see. You guys are doing well today, absolutely. It's C. Okay, because to get cold water, or to get dense water, we want it to be cold and salty. So what are we doing to the Arctic right now? We're melting land ice, which is fresh water. It's going into the North Atlantic. It's making it slightly less salty. And we're also warming it up. So those things that are happening due to climate change are making the North Atlantic a bit less salty. And so that makes it more difficult for ocean water up there to sink and form this deep water that then circulates around the whole of the world oceans. And so this is this idea. Who's seen this movie? Everybody. Okay, it's The Day After Tomorrow. And I was so excited when this movie came out because it's like, this is what I do. Okay, so we have this crazy idea that the whole ocean circulation could shut down and we could be launched into an ice age. And they did it in a slightly crazy way. They did it in 3 days or something. But the craziest thing is this is actually based on reality. And it probably didn't take 3 days and we didn't freeze sort of instantly sort of 3 kilometers of ice or the sea. But we did see really enormous swings in temperature in perhaps as little as 10 years, which is just basically in geological terms, it's instantaneous. So it's really amazingly fast. And I wanted to show you a little bit of the evidence for this. So we were really surprised when we went out and we started taking sediment cores from the North Atlantic, because every now and again we'd find not enormous rocks, but sort of pretty good sized sort of gravel or sand grains right in the middle of the North Atlantic, and we couldn't imagine how on earth we could get some sort of sediment that size out into the North Atlantic. Storms don't really take things that far. Rivers don't end up sort of transporting sediment that far. So how do we get these out there? And the answer is by icebergs. If we have all of this sediment and rock in our sort of ice coming off the continent, and those icebergs float out into the middle of the North Atlantic and gradually melt, then as they melt, they release this sediment and it sinks down, and we get sort of signals of that as we look at sediment cores from the deep ocean. And funny enough, when we looked at our Greenland ice cores, and we'll come on to talk about that towards the end, but our Greenland ice cores is an amazing record of things like the amount of carbon dioxide in our atmosphere, but also temperature. And we can see that over the last sort of 60,000 years or so, we've seen enormous sort of rapid swings in temperature, backwards and forwards. And this is maybe sort of 10, 15 degrees Celsius. This is enormous, enormous changes happening very, very rapidly, perhaps in as little as a decade. Okay? And so we had to come up with an idea to explain how we could see such rapid temperature changes, and we knew it had to be something to do with ice. And it really only happens when we have enormous amounts of ice up at the poles. It really only happens during our ice ages. And so what happens is that every now and again our big ice sheets surge towards the coast, and they release enormous numbers of icebergs out into the North Atlantic. And those icebergs are composed of fresh water. And so as they melt, they release this fresh water, and they can actually reduce the salinity of the water enough that it stops sinking. And so our enormous circulation of the whole oceans just switches off. And it switches off until we can get that water in the North Atlantic to be salty enough again that it can start. And so all of a sudden we just stop transporting heat in the same way we've done that. And so we don't get this sort of nice warm current returning up to the North Atlantic. It doesn't sort of make it as far north as Greenland and Iceland. It perhaps sort of heads off more around Spain. And so we see really dramatic changes in temperature, specifically around the North Atlantic. Okay? And so the last time this happened was geologically really recently. It's called the Younger Gyres, and it happened about 12,900 years ago. And really, we were emerging from the Ice Age at this time. We were nearly towards temperatures of sort of today. And what happened was that we had this enormous lake formed in North America from the melting of these gigantic ice sheets that we had there. And you can see Lake Superior down here for scale. So this lake was truly enormous. And all of a sudden, it broke through into Hudson Bay, and it catastrophically drained, probably in a few days, into the North Atlantic. And so it really dramatically altered our ocean salinity again, and it stopped that ocean circulation. And so Europe and North America went back into an ice age, and it affected climate worldwide, but specifically those places went back into an ice age for another 1,000 years before we could actually sort of lastly come out of the ice age and into our warmer period today. So we know that this has happened. We know that this has happened in the past. And so when we found this out, perhaps in the 70s and 80s, we were really very concerned that the climate change that we're causing today might do this again. And so we would, instead of having global warming and warmer temperatures to contend with in Europe, we might actually get a return to more ice age conditions. And the good news for us is that it's really very unlikely. We just don't have enough ice and fresh water up there, and it's not being released quickly enough for us to realistically shut down the ocean circulation completely. What we don't necessarily know yet is just how sensitive it is, so it might well slow down. We think that it may well slow down, and that will do funny things to temperatures around the North Atlantic. But it's really difficult to study this system. You have to study the whole of the Atlantic and how it's moving. And that's just really difficult to do scientifically, okay? So as we do see melting of ice, as we do see warming of the ocean, then we may well see changes in our thermohaline circulation, but they're not likely to be the catastrophic version. So in answer to my question, it's not worth buying snowshoes just yet. I think we'll be fine, but it's something to be considering. Okay, that's it. I will see you on Wednesday for your midterm.